So as promised, let's revisit this circuit from a previous video and see if we can simplify the process using our impedances. So we're still looking to find our transfer function. Note our output is still defined as our inductor current and our input is still defined as our current source. So our transfer function should be the same because our input and output definitions haven't changed. So note that this is our circuit in the time domain. Everything is a function of t. But if we want to convert our elements to our impedances, essentially what we're doing is we're converting this circuit to our frequency domain. And that's basically what we're doing is we're moving our circuit to the frequency domain as opposed to writing equations in time and then converting the equations themselves. So let me go ahead and paste this circuit here, and then let's just modify it a little bit from here. So of course all of these functions are now going to be functions of frequency, functions of s, as opposed to functions of time. So our I of t, our source, is now going to be capital I of s. If we want to talk about this voltage, which is across all elements, that's capital V of s. Our inductance, L, from our previous circuit, we're going to replace with our inductor impedance, which we found in our previous video to be S times L. In this case, we're just working with variables, but of course you could see how in an actual problem you might have numerical values as well. So maybe for this inductance, we have a value of 200 millihenries. So then we'd have 200 millihenries times S for our impedance. And as we'll see a little later on, our S is basically dependent on the frequency of our source. Okay, so it sort of got on a little tangent there. So let's do the impedances for our other two elements. Our resistor impedance is just the resistance, and our capacitor impedance is 1 divided by S times the capacitance, so 1 over SC. So now we have our circuit in the frequency domain. So the key thing to note as we're doing this analysis is that our impedances we can treat the same way we treat resistors in our time domain. So impedances can be treated like resistors in our time domain. And so the reason is because remember we had that Ohm's law for phasors. We had said that our V of S equals I of S times Z of S. And so let me go ahead and label our inductor current. So now this is capital I sub L of S. Okay, so let's do the same process. We're still using our node voltage. Notice I still have my node 1 labeled, my reference node labeled, my V1 labeled. And as we had said before, we're only going to need one equation because we only have one non-reference essential node. And so remember, we're essentially just doing KCL. So sum of currents in equals sum of currents out. So our current in, we now have I of S from our source. Our current out, so our I sub L, our inductor current, is just going to be V divided by Z. So essentially just rearranging this. For this case, we're looking for currents. So we can say currents are equal to V divided by Z. So in this case, we have our V divided by S times L. And then of course we can do the same basic thing for our resistor and the capacitor because we're using this Ohm's law for phasors, so our impedances are just treated like we treat resistors in time. So we now have our current through the resistor is V over R, and our current through the capacitor is V divided by 1 over SC. So we can factor that V out, so we have V times 1 over SL plus 1 over R plus SC. Okay, so far this is looking pretty easy, but we notice that for our transfer function, our output is the inductor current and our input is the current source. So in this equation, we have our term that corresponds to our current source, but we do not have our inductor current. We do, however, have the voltage, which we can relate to our inductor current. So that's what we're going to do in the next step. So we can say our voltage is equal to our inductor impedance times our inductor current. Again, just using our Ohm's law for phasors. So now we want to substitute that in. So let's substitute this expression for V into here, and what we get is that our I of S is equal to IL, and then if we multiply that SL through, we of course just have 1 for that first term, plus SL over R plus S squared LC. And now it's just a matter of rearranging to find for our transfer function. So our transfer function g of s is defined as our output, and again, I'm kind of being loose. Sometimes I'm dropping r as a function of s. So it's our output I sub l divided by our input I, which is just equal to 1 divided by LC times s squared plus L over R times S plus 1. Oftentimes it's useful to have this coefficient in the denominator for our highest order term be 1. So if we want to do that, we want this to be s squared. We see we're essentially just dividing through our denominator by LC. So this second term then becomes 1 over RC times S, and our constant is just 1 over LC. And since we divided the denominator by that, we need to also divide the numerator to get 1 over LC. And so of course we can see that this is the same result that we got in the previous video, but hopefully that was a whole lot less painful than all of those sort of tricks and games we were playing to get our expression in the time domain. So what we're going to look at in the next video is we're going to look at a generalization for more complex circuits so that you don't necessarily need to be super familiar with the node voltage technique itself. And then we're going to look at one final example in our circuit analysis before moving on to mechanical systems.